Hello, everybody, and welcome back to applying the 7 steps of data analysis to produce a quantitative research study. William Bannon of StatsWhisperer back with you. Okay, today's presentation, we are going to review part 3 of our 7 steps of data analysis textbook, which concerns the data analysis concepts you need to know. We're going to present 9 of them. Also, we're going to do the final selection of the class, or, if you so choose, individual quantitative study project. Lastly, we're also going to review step 1 of the 7 steps of data analysis, the study map for sample studies 1 and 2. Okay, so in the context of the 7 steps of data analysis, we are going to review at the end of this presentation, step 1, the study map. Now here we go. The data analysis concepts you need to know. So any good solid knowledge of data analysis would concern knowing each of these terms and content. Okay, so instead of describing them here, we're going to go through them one at a time. All right, the first term you need to know, the difference between parametric and non-parametric statistics. Parametric statistics are statistics that make assumptions about the data, frequent assumptions, right? For example, the normal distribution that we've mentioned earlier, right? And some examples of parametric statistics we'll use are the t-test, correlation, and ANOVA. So we'll be getting into all that much more heavily. Non-parametric statistics are tests that examine, often by rank, the relationship between variables, but without making as many assumptions, right? An example of a non-parametric test we'll use is the chi-square. Now, one important point to keep in mind is that when your data does not meet the assumptions of parametric tests, right, such as the normal distribution, at times you can substitute the non-parametric equivalent of those statistical tests. So they're very useful. Many times that has to do with sample size, by the way. So many times if your sample is so small that you can't meet the assumptions of the parametric test, like a normal distribution, because you don't have a lot of scores, you might do the non-parametric equivalent with the small sample. And if it's right on the line where you're not sure if you have enough for a parametric test or the assumptions are just on the line of being met and not met, you might actually do both of a way of validating each. Now also keep in mind, non-parametric tests are also used when the method is appropriate, right? Such as the chi-square we'll be using, right? So they're not just tests that are a substitute for parametric tests, they're tests that we would use anyway, right? Now, descriptive statistics versus inferential statistics. Now recall, descriptive statistics are also called univariate statistics, which we examined earlier, we discussed as a step in the 7 steps of data analysis. And so those are statistical procedures that are used to describe the characteristics of a sample or a population. Remember, we had the univariate, and it described the characteristics of one variable, uni meaning one, var meaning variable. Inferential statistics are statistical procedures that test the association between variables. Right? So A is related to B. So these statistical procedures are used to make predictions or inferences about a population based on the observation made through the sample. So we can make that a little clearer. Right? So, for example, descriptive statistics or univariate statistics describe the sample or population. So gender is a variable by itself. So if we have gender in our sample, we might describe that variable as 40% male and 60% female. Right? If age is a variable, we would describe the characteristics of that variable alone, such as M, meaning mean, is 40.5. So the average person, the mean age is 40.5, 40 and a half years, right? The standard deviation is 2.1, min-max, so oldest and youngest is 21 to 78. And there we have happiness again, as we described the characteristics of that variable earlier. Now, the inferential statistics. Right, so we're making inferences about a population based upon the sample. So you can see on the left, the smaller blue circle on the left is our sample. So we might have a sample size of 100. And among our sample, we do an inferential test, right, that indicated among our sample, the blue writing below, happiness is related to personal income. So that's the finding within our sample. So we're going to infer, right, that this finding that was true for our sample is true among the study population, right? So the sample is a subset of the entire study population. So you see our sample is 100. Our population size, and this is just for an example, might be 1 million, say n equals 1 million. So what we're saying is because we found that happiness is related to income among our sample of 100, we're using these tests to infer that this association of happiness and personal income is also true among the study population of 1 million people. So we're inferring our findings in the sample are true for the study population. So that's where the inferential statistics comes in. Now, level of variable measurement. This is a key one because as you can see on the bottom, it says, many essential decisions in analysis are based upon level of measurement. And that's true, right? So we're going to consider 4 levels of variable measurement. So you have to know these inside out. Thankfully, they're pretty simple, okay? So we're going to discuss nominal, ordinal, interval, and ratio. So number 1, nominal. Nominal is a categorical variable where the categories can't be ranked, okay? A good example of this is gender. There's categories of male and female, and one can't be ranked over the other. The same with race. There's racial categories, A, B, C. They're different categories, but they can't be ranked one over the other. They just are the way they are. Now, ordinal, that is, number 2, ordinal is a categorical variable where the categories can be ranked, such as fair, good, or great. So if you were rating a restaurant, you could rate the restaurants by fair, good, and great. So they're categories. You're putting the restaurants in categories of fair, good, and great, and you can rate the restaurants, right? And there could be a hierarchy of those categories. One thing to keep in mind is there's not an equal distance in between measurement points. For example, there's no reason to believe that there's the same distance in rating between fair and good and great, right? So you might be pretty fast to distinguish between a restaurant being fair and good. However, it might have to be much, 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 much better to go from good to great, right? So there's not equal distances between measurement points. We have a special mention here, a shout out for the term dichotomous, right? Dichotomous, you'll hear a lot. It's a categorical variable with 2 categories, such as yes, no, good, great. It could be nominal or ordinal, right? It could be ranked or not ranked. That's okay. It's just a categorical variable with 2 categories, meaning dichotomous. All right, number 3, interval. The interval level of measurement, right? So the interval measures along a continuum with equal distances between measurement points. Remember, ordinal didn't have those equal distances between measurement points, but the interval does, right? So you take an IQ score, right? The distance between 90 and 100 is 10 points. The distance between 100 and 110 is 10 points. So there's equal distances between measurement points. Also, if we consider the subsection A, it's measured along a continuum where higher scores equal more of that construct. If you're talking about an IQ score, it's more intelligence. So higher scores equal more intelligence, lower scores equal lower intelligence. That's called a continuum, and that's how an interval is measured. The same with our dependent variable happiness. 1 means the least amount of happiness, and as you go up to 5, there's a greater amount of happiness. So that's an interval measurement, right? Important to keep in mind, interval does not have, subsection C, does not have a true meaningful zero, right? So in the case with IQ scores, if you get a score of 0 on the IQ test, which it doesn't actually go to 0, but if you got the lowest score or a 0 itself, that doesn't mean there's a complete lack of intelligence. So there's not a meaningful true 0. Now the distinction with number 4, the ratio level of measurement, is that there is a meaningful true 0, right? So ratios measured along a continuum, the same as interval, with equal distances between measurement points, but with a meaningful true 0. So weight is a great example, right? So subsection A. So if we measured something in weight, it would be along a continuum from 0 on up to however heavy the heaviest thing in the universe is, right? B, there's equal distances between measurement points. From 90 to 100 pounds is the same from 100 to 110. And C, there's a meaningful true 0, where if your weight is 0, it does indicate a complete absence of weight. Now, another special mention, right? In real-world research, variables are often called categorical or continuous, right? So they're called categorical when the level of measurement is nominal or ordinal, right? They're in categories. Whether it's ranked or not, they'll just say categorical variable. And they'll call the interval or ratio levels just a continuous variable. So you'll hear these terms a lot too in our program, categorical and continuous, just sort of an abbreviation for these 4 terms. All right, next, getting into measurement, the measurement of our variables, right? So we have the single versus the composite item scores. Very interesting. So the first to consider here is the single item score. This is when one item, perhaps on the survey, one item will reflect the variable measurement. Right? So if we're talking about highest level of education completed, we might just have the one item here that says highest education level completed and asks about A, B, and C. Is it high school GED A? Is it B, college? Or is it C, graduate school? So that's a single item measuring the variable education, specifically highest education completed. Now, the composite item score is a score that's based on multiple items being combined. For example, say we wanted to measure a variable like mood. Well, mood has several dimensions, right? So maybe one item, such as in our education, wouldn't capture the many dimensions of mood that we'd like to look at, right? So consider the 3 items below, which would be combined to measure mood. So I feel happy, number 1, number 2, glad, number 3, good, right? And then each rated on a 1 to 3 scale, right? So through combining these items, we can have multiple dimensions of the construct mood pardon me, in our measurement, right, which is ideal. So say we sum them up, right? So if we sum them, the highest score would be 9, 3, 3, 3, and the lowest score would be 3 if it was 1, 1, 1, right? So 3 to 9, with 9 equaling the more positive mood. So that's a composite item score. All right, study variable type. Very, very, very basics, right? So this is where it all starts. So our independent variable, right, also called a predictor variable, that's our variable of interest that we believe explains the dependent variable, right? So in our sample study, the dependent variable is happiness. And we believe whether you live with a cat or a dog, that's going to explain your level of happiness, right? So that's our independent variable. Then next, the dependent variable, also called the outcome variable, is the variable being explained or examined, such as we said, happiness. We're trying to explain happiness. Now, very important and discussed not as much as the independent and dependent variable, but very important are the covariate variables, also called predictor or control variables, right? Those are the variables in the data set that aren't the study focus, but they're included in analysis because they have an impact on the dependent or independent variable, right? So as we said, if we're looking at income, right? So if we're looking at happiness, we believe income also impacts happiness. So in addition to looking at whether you live with a dog or a cat, we also want to include income because we believe that impacts the dependent variable also. Right? So the influence of the covariate variable is what they call controlled for. So we can better observe the relationship between the independent and dependent variables. Right? So our study question, right? We're addressing, if the independent variable, do you live with a dog or a cat, relates to happiness. And that's expressed in the box on the left, independent variable, with the arrow going to the dependent variable. How does the independent variable impact the dependent variable? But the covariate variable income level may also impact happiness. So how can we figure that into our formula? Our issue becomes whether living with a dog or a cat relates to happiness after controlling for the impact of income level, the covariate variable. Income level could, and that's an operable word, could, because we don't know unless we test for it, right? Income level could have such a dramatic effect on happiness that whether you live with a dog or a cat may not matter at all, right? Or income could have a dramatic effect on happiness, and living with a dog or cat could also have a dramatic effect on happiness together. But we don't know, perhaps, if income overshadows, the pet ownership unless we control for it in our model. So this is what we would do. We would set up a regression model, which we'll get to later, where we can control for the impact of income on happiness. And while that's controlled for, we can then note if living with a dog or a cat impacts your level of happiness after the effect of income has been removed. So that's our covariate variable. Right? So we always want to control for as many covariate variables as possible that impact our dependent variable. So once we control for all those, we can say that the independent variable impacts the dependent variable over and above, all the other influences, which is key. Okay, now the clarity of the study hypothesis. This is an important one because the study hypothesis is like the bullseye, right? We're trying to answer this research question and hypothesis. That's the bullseye. That's the target we're trying to hit. And if you have a fuzzy target, it's hard to hit it, right? So we want a clear study hypothesis so we could get it dead in the center, okay? So number one, when you're doing your study hypothesis, please present one relationship at a time. Right? Consider this hypothesis. People living with dogs are happier, healthier, and more optimistic than people living with cats. This is actually three hypotheses being introduced as one. Right? So this is actually what this is. It's three hypotheses. The first one is people living with dogs are happier than people living with cats. Right? 2, people living with dogs are healthier than people living with cats. And 3, people living with dogs are more optimistic than people living with cats. You always want to be able to say if the study hypothesis was supported or not supported. So what if they are happier but not healthier? Then the way we originally had that hypothesis, you couldn't say if it was supported or not. You'd say it was partially supported, which isn't ideal. You want to say if it's supported, yes or no. So that's why we would break it up into 3 hypotheses. Right? Make the cause and effect relationship clear. Right? If you're stating a cause and effect relationship. Sometimes you don't. Sometimes you just say A has an impact on B, and you might not say what the effect is. But many times we are saying what the cause and effect is, and we can phrase things in the if-then form. Even if you don't present it in the if-then form, it's good to be able to. Even if it's not used in the actual study or proposal, just give it a try to make sure it's solid. So we might say, if a person lives with a dog, then he or she will have a higher level of happiness relative to a person that lives with a cat, right? If, then. And we want to be specific, right? We don't want a blurry target. We want to be specific about the variables being examined. So a vague hypothesis might be the type of pet owned will be significantly related to levels of happiness, right? So it's a little vague. More specific would be people who live with a dog have a higher level of happiness relative to people that live with a cat. And so the more specific it is, the easier it is to answer. All right, now here's one that you don't hear often, right? So you hear the dependent variable stuff quite often. The 3 dimensions of a relationship, you do not. So there are 3 dimensions of any variable relationship. So variable A and variable B, right? Such as living with a dog or cat related to happiness. There's going to be 3 dimensions to the relationship between those variables, right? 1 is significance. 2 is directionality. And 3 is magnitude. So whenever you look at a variable relationship, you should think, you want to look at the significance, the directionality, and the magnitude each time. Now significance, otherwise known as statistical significance, right, reflects the probability of how likely a relationship is due to chance. And the common standard in social science and many medical studies is 5 in 100. So if you've ever seen the P is less than 0.05, that's what that indicates, that the statistical significance is less than 0.05, and that usually indicates it's statistically significant. But you might ask, what does by chance mean? So it means 5 out of 100 times it happens by chance, but what does by chance mean itself, right? So by chance basically means that it appears that there's a significant relationship, but there really is not, right? So in statistics, what we're saying is that 0.05 reflects that we're willing to accept that 5 out of 100 findings, right? So findings meaning SPSS tells us we have significant findings. 5 out of 100 times, they're not really going to be significant, but just random or by chance. So you might look at by chance this way, right? So let's take a practical example. So our example, a man in the office is asked to hold a slice of pizza by a client who's signing a form, right? A coworker approaches him and assumes he likes pizza because he's holding the slice, right? Someone's holding a piece of pizza, they must like pizza, right? However, the man says, no, I don't like pizza. You just happen to see me holding the slice by chance, right? So we even use that in our own vernacular. It just happened to be by chance, right? So what that means is the relationship looks significant, but in reality, it only appeared that there was significance. We sort of got faked out, right? So that's what it means when it happens by chance. It's kind of a random occurrence that looks significant, but it's really not. So in statistics, we accept that 5 out of 100 times we're going to get a finding that says it's significant, but it's only going to occur by chance. Just like the example with the pizza, right? So maybe 5 out of 100 times you see someone holding pizza and they don't really like pizza. Maybe they're holding it for someone else. Like it appears significant, but it's really not. So the key message to keep in mind when we're doing our quantitative data analysis is for each test, each inferential test, you're going to see a p-value, the probability. So if p is 0.05 or less, it's a significant relationship. If p is greater than 0.05, the relationship is not significant. So that's the first dimension of the relationship between variables we'll note. And that's often the most focused upon dimension. So you may have heard it before, but okay, 2. Directionality. So directionality, the relationship between two variables is either negative or positive. What does that mean? So a positive relationship between two variables means as one increases, the second increases. It's positive. They go along together, right? For example, if we're looking at income level and happiness, and there's a positive relationship, that means as income increases, 100,000, 200,000, 300,000, happiness scores increase, 1 to 2 to 3 to 4 to 5, the highest level of happiness. That's a positive relationship. A negative relationship is as one variable increases, the other decreases, right? So a negative relationship between income level and happiness means as income level goes up, right, 200, 300, 400,000, happiness scores actually go down. So they'll go from 5 to 4 to 3 to 2 to 1. So they go in the opposite directions from each other. So that's directionality. So directionality is usually indicated, right, by a minus. So a negative relationship is usually indicates two opposite directions, and that's usually shown by the presence of a minus sign in front of the statistical coefficient, right? So you can see here as an example, we have the Pearson's R correlation coefficient, and R equals negative 0.35. That's a negative relationship because there's a minus there, right? If the minus is absent, such as the term in the bottom where R equals 0.35, no minus sign, that would indicate a positive relationship. So to sum that up, when there is a minus sign, right, there's a negative relationship versus no minus sign, which would indicate a positive relationship. Okay, now the third dimension. This is the least focused upon, but is tremendously important. Number 3 is magnitude. So there's an emphasis in the literature and in the field itself on significance. The p is less than 0.05. And usually that's where the research stops. It'll say there's a significant relationship and the research stops there. However, you also need to consider magnitude, because you can have significant relationships that have a great magnitude and significant relationships that have a very small magnitude, right? So magnitude reflects the strength of the relationship between the variables, how impactful one variable is upon the other, right? So the magnitude of the relationship actually can be measured in several ways, including the effect size. It's a very common way to examine magnitude, and that's what we will look at here. So, as we said, this can't be said too many times because it really needs to be embedded in the field. A relationship between variables might be statistically significant. P is less than 0.05. But there might be such a small effect of one variable upon the other that the finding is almost inconsequential, right? So effect size is a huge consideration that is frequently not considered. For example, if we are looking at factors that impact our happiness, there are several things we could consider, right? Things that might be very impactful, such as how much money we make, our income level, and things that might be less impactful, such as the weather, is it raining, or having a bad hair day. Now, for the sake of argument, let's say we looked at things that impacted our happiness and discovered that all three had a significant effect on our happiness: income level, weather, and having a bad hair day. Now, most research would stop there and say they're all significantly related to happiness, right? But consider this. Okay, now on the left, we have our predictors, right? Income level, weather, and bad hair day. On our right, we have happiness, what we're trying to explain, right? Now, you might imagine that income level has a large effect size, right? You see right above the line, connecting income level and happiness, has a large effect size on our happiness, right? If we don't have enough money for the necessities of life, right, that's going to impact our happiness. Now, weather might have a medium-sized effect on our happiness. Say it rains and you get your shoes are wet and you're all soggy, you might be less happy than if not. And then having a bad hair day might have a small effect size on happiness, right? So that's the point. They all three might be significantly related to happiness, but they have a different impact, right? You could say that if you didn't have enough money for the necessities of life with income level, really the weather and the bad hair day might not even figure into your formula of happiness, right? That would be because income level would have an overarching large effect size on your happiness. So, to sum it up, we can think of magnitude, the third dimension of the relationship, as a small effect size, a medium effect size, and a large effect size. And we'll get into how to measure those when we do our inferential tests. Now, the relationship between variables is just like the relationship between humans, right? So if you have a relationship with another person, sometimes they'll do something nice, and you'll have to savor daily miracles, right? So SDM, that's a good way of thinking about a relationship, right? And in this case, a relationship between variables. S, significance, D, directionality, and M, magnitude. So whenever we look at variable relationships, we're always looking at the SDM dimensions. Alrighty, the Russian doll effect of data analysis. If you've not seen these before, these are classic Russian dolls. The small one fits into the next size up, and that one fits into the next size up, right? And they each fit in one another, right? So the larger one contains a series of smaller dolls. Now, how does this relate to data analysis? All right, you'll see. Once we actually start doing these procedures, that every procedure has a bunch of smaller procedures within it, and those procedures also have smaller procedures within those, and so on, just like the Russian dolls, right? So take the first doll, well, if you could call it a doll, the first column with the head on it on the left, right? The 7 steps of data analysis. So there's 7 steps. And then if we take, for example, step 3, checks of data integrity, and we take that out and open it, right? Then the next column to the right, step 3, checks of data integrity, there's 4 checks, right? 1, statistical power, 2, test assumptions, right? And then if we open test assumptions, number 2, and then that's the third column on the right, right? We open test assumptions, and there's 6 test assumptions to make, right? And if we took the first test assumption, normality, and open that, that would be the final column, right? You'd have to look at normality, and there'd be 3 dimensions of that, skewness, kurtosis, and outliers. So you'll see each of these procedures are like Russian dolls. You just take one and open it, and there's more within there, and so on. Okay, now, haste or paste, save your syntax. So you'll see when we do SPSS that there's an option to either click OK and it runs the test right away, or you could click paste and it creates a syntax for the test that can be saved, and then you run the test by highlighting the syntax and running it. Now, the syntax is very, very useful, so I would recommend not to have haste, but choose paste, right? And save the syntax. Now, why is the syntax so useful, right? Well, first of all, it leaves an electronic paper trail, right, showing that the tests were conducted properly. Because you may do a test and think you used one variable when you used another, and if you have the syntax, you can actually look in that paper trail and see if it was done correctly. Also, the second bullet, the test can be repeated just by running the syntax instead of redoing every single statistical test. So you do the test once and paste the syntax, and if you want to replicate the test, you highlight the syntax and click run, and the entire analysis is repeated. And then third bullet, the tests are more easily transferable into other software programs. So if you want to take your SPSS syntax and adjust it to run in another software such as SAS, you could do that. All right, now on to our second topic, right? So we just want to make sure the final selection of the class or individual quantitative study project has occurred, right? At this point, we should have that project, right? And specify if it's at the individual or class level, if we're using primary or secondary data, and so on. And we should take that information, right? Take that structured study, whatever the topics are, and you should fill in your study map, right? We'll look at our study map for sample studies 1 and 2 right now. So remember step 1, right? That's in the 7 steps of data analysis, the mapping of relationships. On the right, we have our data analysis again, and our step 1 data map, where we're saying we have the bachelorette, and we're relating the relationship between each of the 5 bachelors on the left to the bachelorette. In data analysis on the left, the left-hand column, we have our study map, step 1 study map, and we're looking at how each of these variables impact happiness. What's the relationship between gender and happiness connected with that arrow? What's the relationship between education level and happiness and income, right? And then finally on the bottom, our independent variable, living with a dog or cat, and happiness. So that's what we're examining. Now specifically, the step 1, the study map, presents the variable relationships under study in the form of the research questions and hypotheses in addition to the diagram, right? So we're expressing the study map both in a text form and a diagram form. And we'll do that right now for sample studies 1 and 2. So keep this in mind because you should fill in the study map for your study again. So let's consider sample study 1, which is a quantitative study with a continuous dependent variable, right? So if the 7 steps of data analysis is applied to conduct a study with an interval/ratio level dependent variable, remember that's what continuous is? It's the interval or ratio level of measurement, right? So you'll see the study map is great for clarity and organization. It really lets you hone in on what you're examining, and also, importantly, it lets others see what you're examining too. As they say, a picture's worth 1,000 words, so you'll see that in our diagram. So the research question for sample study 1, right? Are people who live with dogs happier than people who live with cats, right? Our hypothesis is that people who live with dogs are happier than people who live with cats. Our dependent variable is happiness, and our independent variable is, do you live with a dog or a cat? And our covariate variables, right, that we believe might have a significant impact on our dependent variable happiness are education level and income level. Right, and we can put it in a simple diagram to express our whole study in one diagram, right? So we have the covariate variable 1 at the top, education level, and the arrow impacting happiness. Covariate variable 2, income level, the arrow impacting happiness, and finally the independent variable, do you live with a dog or a cat, impacting happiness. Right? So we have mapped out what we're examining. So if you were to apply to your study, right, you just enter your research question, enter your hypothesis, enter your dependent variable, independent variable, and covariate variables. Right? Simple. As we said, these are meant to be templates for you to put in your variables so you can follow along and implement your own study by example. And of course, your diagram too, right? So you would just plug in on the left, your covariate independent variables in those boxes and your dependent variable on the right. Now, sample study 2, if you recall, is a quantitative study with a categorical, in fact, it's dichotomous, it's yes, no, dependent variable, right? So the 7 steps of data analysis are going to be applied to conduct a study with a categorical, right? Yes, no, 2 categories, dichotomous, level dependent variable. So just some slight changes here, slight but very significant, right? Are people who live with dogs more likely to be happy, right? Happy, yes, no, relative to people who live with cats. And the hypothesis is people who live with dogs are more likely to be happy relative to people that live with cats. Now our dependent variable here is dichotomous, happy, yes, no. The independent variable is the same, do you live with a dog or a cat? And the covariate variables are the same, education level and income level. And of course, we have our diagram, and the only thing that has changed is our dependent variable now on the right is happy, and it's categorical, yes, no. Now you'll see through comparing these studies that just this change in measurement of the dependent variable from continuous to dichotomous makes a big difference in the procedures you apply for the studies. That's why we're doing that. Right? And again, if you have your categorical dependent variable, you would plug in your research question hypothesis and variables, and also you would do the same thing with your study map. Okay, now the next class, and we're going to discuss step 2 of the 7 steps of data analysis, data entry, which is essentially entering the data from the survey hard copies into the SPSS database. We'll also learn how to create an SPSS database, right? We'll discuss coding the data, making a data dictionary, the process of cleaning the data, and recoding variables. Right, so in the context of our 7 steps of data analysis next week, we're at step 2, data entry. All right, thank you for watching, and I will see you next class.